Hey, what's up, guys? Yeah, so today I talk about the theorems, a theorem in complex analysis called the Rouche's theorem. And this theorem is not so commonly used, but still some people will use. I think it's written in the complex analysis textbook for the undergrad, but seldom tell the proof. Also, in this video, I'll give some small examples and I'll give the proof. Okay, so let's start. And if you want to see more complex analysis exercise or some theorem proof that I make my video list, you can check out below. Hope you guys subscribe to my channel. Okay, so describe the theorem. So idea is that you have imagine that you have a simple closed curve and on complex plane. And so it's C, and then there's a domain D. And then you have two functions where f and g are holomorphic. So the first condition is that holomorphic in D. And the second condition is that g, the absolute value of g is less than f of z on gamma. Okay, so D is the domain enclosed by gamma. So D is an open set. So we require f and g are holomorphic in D and g less than f on gamma. Then f plus g and f have the same number of zeros inside. Okay, so you need to count the multiplicity. Multiplicities. Okay. So this is the theorem, and the proof is using the so-called argument principle. So if you don't know what's argument principle, you can check out my other videos. But I will directly use it. Okay, so argument principle basically is just say this: if you do the derivative on f, let's say you take a holomorphic function, a meromorphic function, do this, and then with a simple closed curve over 2 pi I, then this will be the number of the zeros. So there is 0f and then minus a number of pole f. So number of 0 minus number of pole. So simple example will be the simple example will be so-called Whiting number. So gamma over 2 pi I. So if you take a curve, simple closed curve enclosed 0, then you should get a pole, right? So you will get 1. Okay, so it's a number of 0 minus the number of poles. Okay, so this is the idea that this is the idea that we need to use. Okay, so obviously that all we need to show is just to show that we want to prove that f plus g and f has the same number of zeros. So by using this formula, and we also know that f and g are holomorphic in D, so there's no PF. So it's very simple that we should just compute this. By definition, right, we just need to show this guy 0. So our goal is to show this guy 0, and then we can use this argument principle. So we have f prime plus g prime plus f plus g minus f prime f. Gamma. Okay, so we just need to show these guys 0. Okay, so hopefully it's obviously simple. Okay, so here comes the trick. Let's write f plus g into f plus g divided by f. Okay, so usually let's call this capital F. So capital F is defined to be 1 plus g divided by f. Okay, so so this guy can be written as f, right? And this guy will be ff minus f prime f dz. Okay. So let me just write everything here. So let's calculate this term. So this is very simple, right? Just using your Leibniz differential rule. Okay, so it should give you the this one. So you get f prime f, which is f prime f. Okay, so that means n f plus g minus n of f will be 1/2 pi I, comma, 1 plus g divided by f, derivative 1 plus g divided by f dz. Okay, and we want to show this guy is 0. Oracle. Okay, so it's very simple. What else condition that we haven't used is this condition. We haven't used this condition. Okay, so finally, so we have f less than g, greater than g on gamma. Okay, so notice this tell you that this also tell you that f cannot be 0. So which means that 1 divided by g over f is well defined. Gamma. So this integral is well defined, right? Because this guy's a holomorphic. Also, 1 plus g divided by f cannot be 0. So is this stupid. Derivative is on the numerator. So 1 plus g divided by 1 plus g divided by f derivative. This guy is well defined because the denominator cannot be 0 because f cannot be 0. Okay, so 1 plus g over f is well defined. Also notice that this condition tell you that since your f is greater than g, so your 1 plus f g, if you take the real part, so these terms, this let me just this g divided by f, right? This g divided by f, since f is greater than g, right? So if you take the real part, and this guy at most cannot be greater than 2, because the absolute value of f is less greater than g, also greater than 0. Okay. So finally, if we let so let me just go to the final sentence. Okay, we have this. So which tell you that if you map f, if you solve f and map this gamma into complex plane, go to the subset C and then map to C, then you will get this is your gamma, right? And you map this f to be 1 plus g divided by f. This image will be on the right half plane, because real part of 1 divided by g divided 1 plus g divided by f is always greater than 0. So gamma will be mapped. The image of gamma under f will be on the right half plane. So image of gamma under f is right half plane. Okay, so by winding number, now you know, right? This gamma, and you do an integral with along this gamma, but but 0 is here, right? So you don't enclose the 0. So by the winding number, this term, this f prime divided by f, do not enclose 0. You can do the change of variable. You just set f prime to be another function, that you will get something like this. Let's say y equals f, and then you will get something, and this is f alone. Go f image of gamma, so it's a change of variable. Do not enclose 0, right? Do not enclose 0, so it's 0. Okay, because you do not enclose the origin. Okay, so finish the proof. Okay, so this is a Rouche's theorem, and this theorem is that. Let me just give you some examples. So I think that the proof is difficult, but it's example stupid. But we can still try to play around with some stupid example. Okay, so this is very simple. So if you consider, this is like some undergraduate exercise. So if you consider f of z to be this, And claim. So you claim first is that has 5 zeros in the disk, z less than 2. And yeah, and has, I think, has no zeros less than 1. Okay, so how to use Rouche theorem? So this is f, right? So we need to say, so for the first one, we need to come out with another function. Say, let's change a little bit, change the notation a little bit, so that let's call this h. Okay. So how about that? For this one, I choose f to be z to the 5. Okay. And I choose g to be 3z cubed plus 7. So by Rouche theorem, I want to say that f plus g has the same zeros as f. Okay. So all I need to show is that f absolute greater than g on z equals to 2. Okay. So but this is simple. Let's do this. So z to the 5 is 32. Exactly greater than 3 times 2 to the 3 plus 7. Okay, because this is 31. Done. Okay, so very simple. And then for this part, we want to do the same thing. So, but it has no 0 or 1. So I should take f to be, I guess it's 7, and g to be z to the 5 plus 3z cubed. So obviously that f on z equals to 1 is always 7, exactly greater than g z equals to 1, which is less or equal to, so this one is less or equal to 4, because 1 plus 3. Okay, so 7 is greater than 4, so f plus g has the same roots as the same 0 as f, but f is 7. 7 has no roots. Okay, so this is the simple. Okay, and okay, once you have this Rouche theorem, and then we can also example 2 is that use Rouche's theorem to prove fundamental theorem of algebra. Well, this is an interesting theorem that any non-zero complex coefficient polynomial has at least 1 root. Okay, so you can prove this by Louvenier theorem. If you know about Galois theory or fundamental group, you can prove it using a lot of, if you know algebraic geometry, topology or geometry, then you can prove it by very powerful technique. Okay, so our idea is I want to show that P has n roots, right? So it's very simple that I can let the rest to be G and F to be AN, Z to N, where N is non-zero. And I can choose Z, where is R to be R large enough. So R can be very, very large, such that F greater than G. This is possible, right? Because when F is, because this is n's power, right? So n is the largest power. So if you choose radius large enough, then obviously that the highest power will dominate. So F greater than G. This will give you F plus G has exactly the same roots as F, where F is here and the P is here. So in this case, it's P. Okay, so this is a very simple example of this route. These two, I think after these 2 examples and this small proof, then you already understand this Rouche's theorem. Okay, see you guys next videos.